Hello students, in this video we'll prove the Fourier series of a function converges to the average value of the function at a jump point. So let's suppose f is 2 pi periodic. I'm going to assume it's bounded for the sake of argument. Bounded interval such that the limit as phi approaches theta from the right, f of phi is f of theta plus, so the right limit exists for this function, and the limit as phi approaches theta from the left of f of phi is f of theta minus. In other words, in principle, f plus can be equal to f of theta plus can be equal to f of theta minus if the function's continuous, but it doesn't have to be for this theorem, which is the beautiful part, right? Then we're going to prove the following. We're going to show then Kn convolution f at theta, at this point theta, will converges to f of theta plus f of theta minus, all divided by 2 as n goes to infinity. Of course, here Kn is the Fejer kernel, right? So Kn is the Fejer kernel. Which is 1 over n plus 1, and the sine of n plus 1 over 2x over the sine of x over 2 squared, which is a non-negative approximation to identity, right? So for these Fejer kernels, we can say what? We know that 1 over 2 pi, the integral from 0 to pi of Kn of x dx is equal to 1/2 because it's an even function, and then the other half of the mass of the Fejer kernel comes between negative pi and 0. Kn of x dx is also equal to 1/2. So both those integrals are equal to 1/2, and they cumulatively add to 1. So in other words, that's the important part of the Fejer kernel. It's an even function, and it integrates to 1, okay, for any n. Now, how are we going to prove this over here? So let's write down the difference of f, k and f of theta, and these values over here, okay? So what can we say? So what's Kn convolution f of theta minus this average over here, minus 1/2 the average of f of theta plus f of theta minus. So it's those averages over there. So I'm going to break this average into 2 parts, and let's see what happens over here. So the first part over here is going to be a 1 over 2 pi, the integral from 0 to pi, and then we're going to have Kn of phi, and then f of phi minus theta, f of theta minus phi, like that. And then on this interval over here, we're going to be able to subtract off what? This over here. So these correspond to values of phi. When phi is negative, you're going from the left. So I'm going to subtract off the what? I'm going to subtract off the left endpoint over here. So minus f of theta minus over here, d phi. And then the second term we're going to get is 1 over 2 pi. 1 over 2 pi what? The integral from negative pi to 0 of Kn of phi. And then f of theta minus phi, f of theta minus phi. And then over here, these correspond to values of theta where you're bigger than theta, so that's going to correspond to the plus limit over here. So I'm going to subtract off f of theta plus over here, where I've used the fact that on each of these half integrals, these Fejer kernels integrate to 1/2, right? d phi, right? So over here, you see that this term and this term is just really just negative f of theta plus, and that's going to give me 1/2, and of course the f of theta plus also has 1/2. So this expression is exactly what we get. Now we're going to do 2 things over here. So now we're at the phase when I'm going to use the continuity, right? So in other words, what can I say? I can let epsilon be greater than 0, and pick delta such that what? Such that if your phi is between negative delta and 0, then f of theta, this will imply that f of theta, and then if I do a minus phi over here, like we have over here, minus phi. These are going to correspond to the what? Plus values. This has to be close to f plus, right? So minus f plus. So in other words, over here, your theta plus something is less than epsilon. And then for the same range over here, phi less than delta implies that f of theta minus phi. Now over here, your positives are going to subtract the negative limit. Okay, good. All right, so now we put absolute values around everything. And that only makes everything bigger, right? So that's going to make everything bigger over here. And now how can I estimate these things over here? Well, I have two terms to estimate. So if over here, if phi is between 0 and what? If phi is between 0 and delta over here, for that range over here, I know that those difference of f and f theta minus, this difference over here between 0 and delta is less than epsilon. And of course, the Fejer kernel is less than or equal to, it integrates to 1. I don't need absolute value on the Fejer kernel since it's not negative, right? So I can say that this first term over here, these first terms over here are less than or equal to 1 times epsilon plus 1 over 2 pi, the integral over all the values of phi that are bigger than delta, so delta less than phi less than pi, of just the Fejer kernel. And now here I'm going to use the fact that these functions are bounded, right? So I'm going to say that there's a bound on f, so we're going to say that f is less than or equal to some constant m over here. That's the boundedness on m. So that's going to be, I'm going to put in a 2m over here, 2m for the bound on those things. That's the largest that those differences can be, okay? And then likewise over here, these terms over here, what can I say about these terms over here? These terms over here, I can do the same trick, is less than or equal to plus. When you're between negative delta and 0, and that range is negative delta 0, we know that these terms over here are within epsilon of each other. So I'm going to get a what? I'm going to get an epsilon. Epsilon. Of course, there's an epsilon over 2 pi, but that's going to be, that's even smaller, right? So I can say an epsilon times what? Times that plain old epsilon plus 1 over 2 pi. Then we're going to have the what? Then we're going to have the integral from what? From negative pi up to negative delta, right? Of just kn, which is not negative, so I don't need the kn of phi, and then times 2m d phi. Again, I'm just putting in an absolute value of kn of phi by force of habit, right? It's always good to leave the absolute value in there because then you know you're correct. And then we're going to use the non-negativity of this function over here later in the proof, okay? Now, what do we know? So we can now say that, what can we conclude from this? We can conclude from this that the lim sup, as n goes to infinity, of kn f of theta minus this ratio over here, 1/2 f of theta plus f of theta minus. Well, what do we know? Since the k is an approximation identity for any delta, these terms over here, this term over here, and this term over here, exactly account for what? Exactly account for the area, these terms over here. And we know since k is an approximation identity, these terms tend to 0 as n goes to infinity, right? So this is less than or equal to 2 epsilon, and that concludes the proof because the lim sup is less than 2 epsilon for any epsilon, therefore the lim sup of this absolute value is going to 0, therefore the limit has to go to 0. Therefore, this implies that kn convolution f of theta converges as n goes to infinity to 1/2 f of theta plus f of theta minus. And this is very useful when the function has a jump. So if the function has a jump discontinuity, this exactly tells me what the Fourier series converges to. In further videos, we'll examine that there's actually an overshoot, and that's known as Gibbs phenomenon. So we'll actually prove there's about a 9% overshoot near these jump discontinuities. Now, what we can also say too now is that we know that whenever the partial sums of the Fourier series, now put in a dn for the Dirichlet kernel, convolution f, will converge to the same thing as the Fejer kernel converges to. So in other words, under the conditions that the function is f is continuous and f prime is continuous, then at any jump discontinuity, we have that the partial sums of the Fourier series, dn convolution f, converge to the same thing as well. It's much easier to prove this is true for the Fejer kernel or for the Abel, or either for these Cesaro means with the Fejer kernel or for the Abel means with the Poisson kernel, because you have a symmetry and an evenness. However, if you put more conditions on the function itself in terms of like continuous differentiability differentiability aside from jumps, then you can also prove the same results for the partial sums of the Fourier series, but this gives you a flavor of how the proof goes in general. Thank you very much.